In order to test how much a column can withstand before it buckles, I will be using this contraption that I built. The slider will be what I will be placing the weight on to test the critical load of the material. The platform as well as the slider contain L brackets that allow me to test different end configurations. This is Euler's buckling formula, and it calculates the load a material will buckle under. In this formula, the E represents the modulus of elasticity, which is given, the I is the moment of inertia, which needs to be calculated, the K is the effective length factor, which depends on the end configurations, and the L is the length of the column. When it comes to the moment of inertia, take into consideration the moment of inertia about both axes. Then use the smallest possible value when calculating the critical load using Euler's buckling equation. A column may sometimes be crushed instead of buckling. Therefore, you should calculate the critical stress, and if that value is smaller than the given yield stress, the material will indeed buckle. Now it's time to start the tests. In the first couple of tests, I will be using a fixed configuration. This will limit rotation and translation. For this test, as well as the others, I will be testing the material of cork. This time I am testing a 10-inch beam of cork. Because the critical stress is less than the yield, this should buckle instead of being crushed. This test is once again using a fixed end configuration. However, this time I am testing a 12-inch beam of cork. Because of the critical stress, it should buckle. In the next couple of tests, I will be using a fixed pin configuration. The pin configuration will only limit translation. In this test, I will be testing the critical load of a 10-inch beam of cork again. Because the critical stress is less than the yield, this beam should buckle instead of being crushed. This is the last test, and I will be working with a 12-inch beam of cork with fixed pin configurations. Once again, the beam should buckle considering the critical stress is less than the yield stress. Here you can see each test with its calculated critical load and the load it actually buckled under in the experiment. In the last column, you'll find the percent error. As you can see, the fixed pinned end configurations had the highest error. This is probably due to the fact that the pin configuration was still acting as a fixed configuration. If you watch the previous two tests again, you'll notice how the fixed pinned beams buckled in a similar way to the fixed beams. Because rotation is free for a pin configuration, the beam should have buckled in the plane that it is able to rotate, which would have been forward or backwards, not side to side. Other errors in this experiment can be due to the fact that the friction between the slide and the supporting beams was neglected, the reading of the load when it was being weighed on a scale wasn't as precise, and the reaction time from seeing the buckling happen to stopping the weight that was being added was slow.